Oh, we left off in the best part, right? And it's now been a week since I've seen you guys, and so of course I'm going to be practicing your names. And I left my cheat sheet in my office. Man, I'm really struggling today. All right. We were talking about hybridizations. Do you guys remember? The atomic orbitals that we were starting with, we said, let's imagine that we just have an atom that has its s orbital, its px, py, and pz, and let's hybridize them in unique ways that give meaningful new orbitals. Orbitals, true or false, are just mathematical equations. True. So when you take a mathematical equation, you can stack it up with another one, and parts of that equation that have the same phase or sign, plus or minus, will constructively interfere, and opposite signs, plus and minus, will destructively interfere. I already gave you guys the combination that we get from S and P. We said 2 orbitals in gives 2 orbitals out. And because we only hybridize one axis, these new orbitals are oriented along that one axis. So this leads to S and P. What I wanted to remind you guys is that the hybridization correlates with the geometry. So sp hybridized atoms are linear central atoms. When you identify that central atom, you'll say the molecular geometry around it is linear because its orbitals, its hybridized orbitals are linear. This had 2 unhybridized p orbitals. We said that it was the py and the pz that remain unhybridized. They do not need to be used for bonding, but if those unhybridized orbitals are used for bonding, then it's used for pi bonding. We took S with 2 p's. We gave this the name sp2, and we did not discuss what geometry this gives, but because I have 3 orbitals hybridized, I get 3 orbitals back out. Because I'm hybridizing the px and the py, I have access to both the p-axis and the y-axis, which gives me an entire plane to orient these new these new orbitals on. So these are oriented along the xy plane, and they spread out as far as they can into the shape of a triangle. So we say that this central atom is trigonal planar. There's one leftover pz orbital. Let me try to clarify that that's what this is a little bit more. This is p times 2. This is p times 1. It doesn't need to be used for pi bonding, but if it's used in bonding, it's used for pi bonding. Okay, the last combination that we didn't get to last class was all 3 of them together, giving us the sp3 hybridized atom. There are 4 of these orbitals. This central atom now has access to all 3 dimensions. This is a 3-dimensional molecular geometry, and we call this tetrahedral. Drawing the linear sp orbitals and the trigonal planar sp2 orbitals is not too challenging, but drawing the sp3 orbitals gets us into more advanced artwork. So without trying to make you guys artists, and without trying to lie as if I've gone to art school for this, I'm actually going to start by drawing a sketch of what this 3-dimensional geometry should look like, and then sketching in the orbitals. But you really don't need the orbitals. What you would do better having is at least the sketch. So we're going to take two lines and we're going to put them at this angle. These lines are in the plane of the board. They're in the same plane as each other. That's representing two of our orbitals. The other two orbitals are also in the same plane as each other, but they come in and out of the plane of the board. So to represent that, we'll show a line that comes towards us, and we're going to fill it in and call it a wedge. This wedge line represents something that is coming towards you out of the plane of the board. This is perspective, and we need to agree on what this perspective is communicating to us. The other orbital, the last orbital, goes behind the plane of the board. This we call a dash. 4 orbitals, 2 sets of 2. One set is in the plane of the board, the other comes in and out of it. And this is where, if you wanted to draw what those actual orbitals look like, you'd want to orient those orbitals in a similar way. But showing the ones that come towards you and the ones that go away from you gets really complicated and messy, and it doesn't really communicate a lot. But I am trying to show you that this has a 3-dimensional shape. Now, you're able to work forwards and backwards. If you can identify a central atom is tetrahedral, then you know that it's sp3 hybridized. If you know that a central atom is linear, then you know that it's sp hybridized. But there are some other ways that you can go around this. So you have this worksheet from last class. I apologize, I didn't bring the rest of them that I had with me. So if you forgot yours, then you can use what's on the screen. We're going to be drawing out some of these structures and assigning their hybridizations. Now, this was all in the scope of valence bond theory. And valence bond theory, remember, actually remind me, valence bond theory tells us what? What is the definition of a bond based on valence bond theory? Yes. And I know your name. It's Bryn? No. Can you remind me? Layla, thank you. Overlapping orbitals. So one of the fundamental questions to us then is, what orbitals are overlapping to give a bond? So we're going to be drawing out the Lewis structures for these compounds. And we're going to identify what orbitals overlap and what types of bonds they give us. Valence bond theory is also going to define for us 2 types of bonds. A sigma bond is a head-on overlap. If orbitals point towards each other and overlap head-on, we call that a sigma bond. A pi bond is a side-on overlap. That means that 2 lobes of 2 orbitals are overlapping side to side. So the nature of the bond will be described by either sigma or pi, as well as what orbitals are used to create that bond. I don't want to spend too much time reviewing how to do Lewis dot structures, because it's not totally the point of this class, and we're going to move past Lewis dot structures today. But the quick reminder is that you count valence electrons for all of your atoms, add or subtract electrons based on the charge. Bond everything at least once, starting with single bonds, and typically you place the least electronegative atom in the center. These are fairly simple structures, although probably some you have not seen in general chemistry. And so rough estimating your Lewis structure is going to get you a long ways. What I'd like you guys to do is try sketching out as many of these as you can in the next 5 to 10 minutes, and then identifying the bonds that are present, sigma or pi, and whether or not, what orbitals are overlapping to give you those. Actually, let's start with this. Start sketching them in the next 10 minutes and start looking for hybridizations at central atoms. For instance, the carbons and the sulfur. If you have questions on it, I'm going to be coming around so I can try and push you in the right direction, but feel free to collaborate. 10 minutes. So at the 5, I'm going to have the answers up on the board and we're going to start talking about them. I mean, do what you think is going to help you. So if you want to take a shortcut, it's okay. It's not going to hurt. Do what you're comfortable with. Up to 6. Good job. Is this for like Excel?
It's for all functions. I actually wish, it's funny that I got it for Excel. But it's like quick keyboard functions for Mac apps specifically. So Finder and that kind of stuff.
Actually, that'd be helpful. That would explain why sometimes I fumble on my keyboard and then random stuff pops up.
It's taught me a few things. I will say I knew most of them. So I was like, I should have got an Excel one or something that I have no idea the quick commands. I get a keyboard protector on every laptop I have, so I figured instead of it just being flavor, I color, I get one that... It'd be like that, right?
Smart.
She's right? I haven't done this in so long.
Yep. Yeah, you got it.
On that last one?
Yeah.
Usually we put the least electronegative atom in the middle.
That's right.
But on this one I know sulfur is...
Sulfur will go in the middle.
Oh, it is? Okay.
Yeah. Sulfur is less electronegative than oxygen. And the solution you came up with, I think, can work, but it's going to be a very troubled molecule.
So sulfur 6? Isn't oxygen 6 as well?
Same family.
Maybe they're strange. Wait, and you said that usually electronegative?
That's right. Other than hydrogen, hydrogen won't go in the middle.
So I feel like you never could we just do that? Well, it's S and O. Oh, right. I don't know. I forget. Is it the higher up it is, the more electronegative? It's like the closer it, right? Yeah.
Up and to the right. You got it.
But you're probably so right.
Jordan, never mind, sorry. I know this last name,
Mortensen?
and I was trying to think of who it was, what former student I had. It was a friend from college. And
From college. Oh, Wisconsin?
yeah, UW Stevens Point.
No, I don't know any Mortensens, but it's a fairly common last name.
I feel like I haven't seen it since then.
Oh, really?
Yeah, which is why I thought maybe I knew who it was.
But like, how many last names are you seeing of? Well,
I mean, I see a lot of last names, yeah.
don't text. What? Okay, wait. Is there a party on both sides? Is that what you did? Yeah, it could make sense. No, that makes sense because then it's 7. And then this would be, so we need 5, 6.
Yes.
So if it's linear, it would be SP.
Good.
If it's got 3 bonds, basically 3 different like connections,
Yeah.
it would be SP2 because it's tetrahedral.
That's
Or
right.
Trigonal, I mean. And then with 4 branches, it's going to be tetrahedral.
Good.
So that would also be trigonal.
Yeah, actually, there's a lone pair on that sulfur,
Okay.
which gives it another region.
Oh, which makes it SP3.
Yes,
Okay.
but it also has a pi bond, which means that it can't really be sp3 because sp3 orbitals can't do pi bonding.
Nothing?
It's either sp2d or it's sp3d. I actually forget. I'm not going to have you guys answer questions like that.
But it would be hybridized.
Yeah.
Okay.
Small suggestion, make them superscripts and not subscripts.
Oh, okay.
sp3 superscript.
Smart. One more question.
Yes.
The pi bonds, there's 2 pi bond possibilities for linear.
Yeah,
Okay, and then 1 for trigonal.
That's right.
And none for tetrahedral.
good.
So this one that is weird.
That's why it's a
would
weird
still
one.
have a pi because it's weird.
Because we see it. Yeah.
Okay, thank you.
You had your hand up? Yes. Great.
Well, I ordered that. I did not.
But you got it.
Perfect. And then, so how do you know that? Can you explain sigma bonds to me? I understand pi bonds.
Sure. So sigma is anytime the orbitals overlap head on to each other.
So this would have 3 sigmas?
No, it's a good question. Actually, the trick that we'll use with a structure is every time there is a bond, there's a sigma bond. Anything more than just a single bond, the rest are considered pi bonds.
Okay, so this would have 1 sigma
Yep,
and then
2 pi.
Okay.
Yep.
We wouldn't count the carbon hydrogen.
That's right.
We would? Or we wouldn't?
Well, this is also a sigma bond
So that's 2 sigma bonds, 2 pi bonds?
from the central carbon.
From the central.
Yes.
Okay.
Yep.
Cool.
So let's say another one. A single bond, that's sigma. A double bond,
Sigma and a pi.
Good.
And then sigma.
good.
Okay, cool. Thank you.
Am I missing something here? Because I count 24 and there should be 26.
Lone pair on the sulfur.
Even though it has
Break its octet. Yep. Hi, Vivi.
To break the octet for the sulfur.
Yep.
So why? Because I know if you did break it, oxygen would be a formal charge of -1 and sulfur would be +1. Is that better than being 0 or +2, 0, 0, 0? Why would it break it?
Well, actually, if you did not break, so what you need to do is place a lone pair here, no matter what. You're short on electrons by 2. So you have to place a lone pair on the sulfur. You could not break the octet by placing that lone pair, but then giving the pi bond back to oxygen. Now everything would still have an octet. No octets would be broken. Oxygen would be -1. Sulfur would be +1. If you keep the double bond and the lone pair on the sulfur, everything is neutral. No formal charge. And that's actually something we'll talk about next week is minimizing formal charge.
That's what I thought.
Yep. That's one of our rules for resonance. All right, are you guys ready? Our first structure, hydrogen cyanide. What is the hybridization of the carbon? Oh, sorry, you have a question? Or you want to answer it?
No, I had a question.
Tell me.
I was just wondering if it matters where you put the lone pair for the nitrogen.
No. In fact, after today, you have the freedom to assume lone pairs. But you know what happens when you assume? You might, yes, you do get it wrong on the active homework. But that's not the funny saying that they have. If you assume, it makes an ass out of you and me, which is how you spell assume. So assumptions are helpful to let us communicate more quickly, but assumptions can also hurt you in the long run if you forget what you're assuming. In Selena, your question, no, that lone pair could go anywhere along that nitrogen. It wouldn't really matter. However, I know the geometry of this nitrogen, so the true shape of the molecule would look more like this. So, what is the hybridization of my carbon atom here? Raise of hands. SP. How can we know that this carbon is SP hybridized? Tell me what you used. Kirsten.
Usually, well, it's in a line, and so it's linear.
It's linear. What if somebody had given it to you like this, though? Because they didn't really know how to start drawing it. Is it linear still? Rachel? And you told me you want to go by Ray. Thank you. 2 sigma bonds, 2 pi bonds. What is the only hybridization that can do 2 pi bonds? SP. Now, let's review, because I know not everybody knows this yet. How do you know that this carbon has 2 sigma bonds and 2 pi bonds? Every time you look at a bonding region, there is 1 sigma bond. No more, no less. If it's a bonding region, there's 1 sigma bond. So this carbon has a sigma bond to the hydrogen on the left, and it has a sigma bond to the nitrogen on the right. Can you tell me what orbitals need to overlap for the sigma bond between hydrogen and carbon? What is hydrogen's orbital? S. So the s orbital of hydrogen is overlapping with the sp orbital of the carbon. Good. Any additional bonds beyond that sigma are pi. So the carbon and nitrogen on the right have 3 bonds, 1 sigma, 2 pi. And again, it is linear, which helps you identify that it's sp. It has 2 pi bonds, which can only be done by sp. sp2 can only make 1 pi bond. sp3 can make 0 pi bonds. It has no p orbitals. The p orbitals are what allow for the side-to-side overlap to create a pi bond. What is the hybridization of this nitrogen atom?
SP?
Also sp. How did you know that? You counted the things around the nitrogen. So one option that we had was count the electron regions. Carbon has 2 electron regions. sp will be its hybridization. 2 electron regions, 2 orbitals need to be hybridized. Nitrogen is similar. It has 2 electron regions, bonding and non-bonding. sp will be its hybridization. Jordan.
Are there ever instances where there could be like 2 bonding regions, but it's not linear?
No. I've never heard of 2 electron regions, but it's not linear. If there's only 2 electron regions, whether they're both bonding or one bonding, one non-bonding, those electron regions repel each other as much as they can, which is 180 degrees, so linear. Additionally, the nitrogen also has 2 pi bonds. And what's the only hybridization that allows for an atom to make 2 pi bonds? sp. Kirsten?
This may not be applicable, or may not be a good time to ask this question, but if you were to extend and like add 2 more atoms to the nitrogen,
Without breaking its octet?
make a good point.
So I could add 1 more, but it could only go here.
Okay, so with actually, yeah, no, you're right, never mind. Okay,
Good.
thank you.
So now we know the hybridization of nitrogen. So can you tell me what orbitals need to overlap to create the sigma bond between carbon and nitrogen? Is it Camilla? Tell me. Just say what you said. And? Good. Because both atoms are sp hybridized, they must have sp and sp orbitals overlapping. The sp of carbon overlaps with the sp of nitrogen. Okay, full transparency, I always get mixed around in these first few lectures because I did this exact same worksheet with my OChem 2 class last week, but we went a lot faster. So I forget if I have said things to you guys or not. Do you think there are better names that we could have come up with than SP, SP2, and SP3? And not names like Frank or George, right? What name would you have given to these new orbitals? What would you have called them? S is a good name because S is a spherical type orbital. So having it called S, that's alliteration, S spherical. P is another good name for a propeller or petal-shaped orbital, P propeller. What would you call these new orbitals? The hybrid orbital that comes from S and P. The hybrid orbital that comes from S and 2 Ps. Honestly, I don't know. SP communicates a lot of information. It's 50% S, it's 50% P. SP2 communicates a lot of information. It's 1/3 S, it's 2/3 P. So they are kind of weird names, and students forget that the number of orbitals that went into hybridizing is equal to the number of hybridized orbitals made. But that name, despite being a weird combination, it is a really useful name. I also want to give you guys a little, I do want to backtrack. I'm showing all of these orbitals kind of separated from each other, but that's to avoid the confusion of showing how they actually take up space. These nodes, where the orbitals go from shaded to unshaded, that's where the nucleus really sits. So if I were to show all of these orbitals in space with the nucleus centered in the same spot, then I would be showing these sp orbitals like this. And now it doesn't communicate the shape or size or orientation of the orbital quite as well because I'm showing them overlapping. They do overlap in space, but it distracts from the nature of the orbital. And then if I tried to add in these p orbitals that also sit here, now it's just garbage. So I've separated all of these orbitals to give you a little bit more context. The creation of these orbitals, I also wanted to show you. The way that we make these sp orbitals is we take S and we take px and we sum them together. So we overlap them in the same region in space. Do you remember what the shading represents? What are we communicating by the shading? Not quite. No, not like the wedge and the dash. Has to do with the mathematical equation. Whether that positive or negative is at the start of the equation. So if I have an equation where both have a positive in the front, that's constructive interference, and they add together to give a larger lobe with that positive sign. If I have a region with positive and negative, they subtract from each other, and I get a region with a smaller area there. And then to answer the question of why do two form in opposite directions, it's because with these equations, they are possible solutions, and there are different ways that those possible solutions can be oriented in space. And so all possible solutions to all combinations of possible solutions are possible, if you get that. The other thing is electrons are weird, so just accept it if you can't understand it.
So
Annie?
Is a positive charge?
Not charge, no. The positive or negative sign on the mathematical equation. For instance, maybe positive means a wave in the ocean is rising above base ocean level, and a negative means that a wave in the ocean is below base level. In terms of the electric wave, the electric field, you could say it's harder to comprehend, but think of it as a wave in the ocean rising and falling in different parts. Does that help? If you took two waves, one that was rising and one that was falling, and you combined them, well, they'd cancel each other out. If you took two waves that were both rising and you combined them, they'd rise even higher. Weird stuff. I'm not even going to attempt to show you how the other orbitals overlap to give you that combination of the hybridized orbitals. This is just where they're coming from. All right, back to it. Where do the pi bonds come from between C and N? The overlap of what orbitals? If it feels easy, then you should say it. P and P. The p orbital on carbon that has not been hybridized, and the p orbital on nitrogen that has not been hybridized. And there are two of them. Two p orbitals, both are a combination of p to p overlap. How about this? What type of orbital is that non-bonding lone pair on nitrogen held in? It's not in an s orbital. Nitrogen doesn't have an s orbital anymore. That s orbital has been hybridized with one of the p's. In a p, it's not in a p orbital. Nitrogen only has two remaining p orbitals, and both of them have been used to do pi bonding. So the only answer left could be it isn't an orbital. That's where the electrons have to be. It has to be sp. Nitrogen is sp hybridized, meaning it has two of those sp orbitals, two pi orbitals. One of its sp orbitals is used for a sigma bond to carbon. Its two p orbitals are used for pi bonds for carbon. Where's the other sp orbital? It's holding the lone pair. Orbitals are mathematical equations that describe the size, shape, and orientation of where electrons are. These electrons are in a size, shape, and orientation defined by sp, 50% s, 50% p character. Deal? These electrons that make up the sigma bond, by the way, it doesn't matter which of these is sigma and which of these is pi, it's arbitrary. The two electrons that make up the sigma bond are overlapping two orbitals that both have sp character. All right, our next structure, CH2. We'll put the carbon in the middle. It is not the least electronegative, but hydrogen can't go in the middle. Oxygen gets two lone pairs. Can you tell me the hybridization of carbon? Tell me how you know it's sp2. Trigonal planar. How do you know it's trigonal planar? Three regions, sp2. 3 regions needs sp2 hybridization. Is there another way? 1 pi bond, which is characteristic of the sp2 hybridization. What's the hybridization of the oxygen? Trigonal planar, meaning sp2, because again we have 1 pi bond and 3 electron regions. This time it's 2 non-bonding regions and 1 bonding. But that's still 3 electron regions trying to repel each other as much as possible. All right. Can you tell me the orbitals that overlap to give me the sigma bond between carbon and hydrogen? S and sp2. That's true on both sides. Can you tell me the orbitals that overlap to give me the sigma bond between carbon and oxygen? sp2 to sp2. And what about the pi bond between carbon and oxygen? P and P. For the purposes of our class, not always true in chemistry, but for our class, P and P is the only way to overlap to get a pi bond. Jordan.
Okay, just to clarify, so with the carbon and hydrogen, you know that the sigma bond is overlapping with the S and sp2 because of the hybridizations of each of the individual atoms. So hydrogen is just in the s orbital, whereas carbon is in the sp.
Good.
So you
Well, not sp, sp2.
so you get S and sp2.
That's right.
Okay, and then I see how you go from
When carbon was sp, the sigma bond was made by S and sp from carbon. Carbon didn't have sp2, it had sp orbitals. When the carbon is sp2 hybridized, the sigma bond between carbon and hydrogen is S and sp2. Hydrogen technically is not hybridized here. It's just, it can't hybridize. It's just S.
because that's what it normally is, like on its own, right?
Yeah, it's in the first row. It only has access to the one s orbital.
So then how do you decide? Okay, so then the oxygen and the carbon are both trigonal planar, so that's where you get the 2 s's, right?
Good.
Can you explain the pi bond again though? That is where it's
Yeah. The pi bond is a side-to-side overlap, which only happens when p orbitals sit adjacent to each other, side to side. Otherwise, all of our other orbitals are coming together. For instance, if I look at this S to sp2, I'm looking at this head-on overlap between orbitals.
And you said pi bonds in this class are always trigonal?
Pi to pi. P to P.
Okay.
Yep. All right, our next one is a doozy. So there's a lot of different ways that you could look at this. You could draw out all of the H's on all of these CH3 groups, or you could abbreviate them as CH3 once you get the gist of it. All of the carbons, Vivi, I see confusion on your face. What can I clarify? Oh, you might have drawn it differently? It can be a little confusing because it says CH3, okay, because it says CH3, 3, I know that there are 3 groups of CH3 connected to one central carbon. All of the carbons here share the same hybridization. What is it? sp3. What about the hybridization of my oxygen? Well, let's count all electron regions, bonding and non-bonding. 2 bonding regions, 2 non-bonding regions, 4 total electron regions that want to repel each other as much as possible. So oxygen is also sp3. How many pi bonds in this molecule?
0.
0. All of the atoms are sp3 hybridized, and sp3 hybridized atoms don't do pi bonding. So there are 0 pi bonds, only sigma bonds, and those sigma bonds here are the overlap of sp3 orbitals with s or sp3 orbitals with sp3 orbitals. For instance, the sigma bond created by carbon to carbon is the overlap of sp3 to sp3. The sigma bond between C and O, it's just getting really cluttered, so I don't know if I'll draw it. C to O is also sp3 to sp3 overlap. Okay, here's what I'm realizing in the moment. I've only given you examples where the sigma bonds are either S to some hybridized orbital or the same hybridization on both sides. Sigma bonds do not need to have the same hybridization. So I want to deviate and give you guys a slightly different structure. I'm just going to give you a snapshot for now. We could imagine that there are other atoms bonded on the rest of this molecule. We really don't need to know what they are. But based on the information we have about these two carbons, one of them is sp2 hybridized, one of them is sp3. Do you agree? What orbitals overlap to give the sigma bond? An sp2 orbital with an sp3 orbital. Easy. Yeah?
This is slightly off track, but it's coming back to the lone pairs. Are lone pairs always going to be sp orbitals by themselves?
No, lone pairs will not always be sp orbitals. Good question. What orbital holds this lone pair on oxygen? We know what orbitals this oxygen has. This oxygen has 3 orbitals that are hybridized sp2, and it has 1 orbital that is p. The p orbital is used up.
Okay.
One of its sp2s,
Going to be sp2. Okay.
that's right. And Britton, on that same note, what orbital holds this lone pair? Kirsten, do you agree? If those are the only orbitals that oxygen has, they're all sp3 orbitals on oxygen, then these electrons must be held in an sp3 orbital.
So the hydrogen to the oxygen would also be an sp3?
Yes, let's do this more. What orbitals overlap to give the OH sigma bond? S to sp3. Great job.
Is hydrogen ever? No, because it's just so it's always going to be.
Hydrogen has no capacity to be anything else. All right, I don't want to spend a lot of time actually on that last structure because mainly it was there to show you that chemistry can be more complicated. But we're not going to be testing on this a lot. Sorry, ever. This was a reminder that some atoms expand their octets, sulfur being one of them. You need to be in the 3rd row. By you, I mean the atom. In the 3rd row or lower. That's because it now has access to d orbitals where it can place additional electrons. The hybridization, based on the rules that we had, 1, 2, 3, 4 electron regions around S, should make you think that it has sp3 hybridization. But we know sp3 hybridized atoms can't do pi bonding. They don't have the capacity for it, which means that this sulfur is either sp2d, where it has hybridized one of its d orbitals to help make all of its bonds and keep its lone pair, or it's something weird like sp3d. I think it's sp2d, but I'm not even going to put it up there because I don't want you guys to think about it. It's not an option you'll have to think of. Just to show you that chemistry is so fun beyond the scope of this course. Kirsten?
Sorry for all of these questions.
Don't be.
I never really understood all this, so this
Great. That's why I do it.
So so you said that sulfur can make 6 bonds. My question to you is, why does sulfur break the rule of the
Octet?
Yeah. And
Comes down to charge.
if that is the case, then why is there only 5, or why are there 5 regions instead of 6?
No, 4 regions.
Well, sorry, there are 5 bonds.
10 electrons. Yes,
Yes, 10
there are 10 electrons around sulfur when it could get up to 12.
Yeah. So why is that the case?
This compound has inherent stability in this way. That is kind of just like a baseline fact. Yeah. And why does it expand? Because it doesn't need to. The oxygen, being more electronegative, could take the pi electrons back for itself, and now everything is at an octet. But now there are formal charges in the structure that needn't be there. And we're going to talk about this rule next week, why we want to minimize formal charge. The relationship between this and the version I just had is called resonance. And resonance aims to minimize formal charge. I don't have a better answer for you, I'm sorry.
It's okay. That's okay.
Okay. All right. So I do want to point out something. Kirsten mentioned this stuff kind of flies over your head in Gen Chem. And you don't talk much about it in Gen Chem 2 at all, is that right? That's one of the reasons I bring it up now, is because it is the fundamental theory of bonding in our atoms. And I've had students tell me in the past that my class is very comprehension-based. I'm aiming for you to understand the fundamentals, and then we'll apply it all semester. So this stuff doesn't go away. It's going to keep coming back, which is why I spend so much time on it up front. Now, the next theory of bonding that I want to introduce to you guys is called molecular orbital theory, otherwise called MO theory. Can I see a raise of hands for people that have learned MO theory before in their Gen Chem lectures? Where'd you go? BYU, okay. I think I heard UVU. No, I think I heard the U does it. Anybody take Gen Chem 2 at the U? But you don't remember it? Okay. So this is not a topic that I test on frequently. Maybe 1 or 2 questions a year will show up on this topic, but it is also a fundamental explanation as to why molecules behave the way they do. So I'm going to be leaning into it to explain things like resonance, to explain reactivity, to explain stability, which means I want you to understand it because it's going to help you understand the other things that you're going to be tested on so much better. Molecular orbital, as opposed to what? Atomic orbital, S, P, or sp, sp2, sp3. Those are also atomic, but they're hybridized atomic orbitals. So can you tell me what distinction an atomic orbital must have from a molecular orbital? Why are they different things? It's in the name. Britton?
The electron pairs of the atomic orbital would be 2 electrons from that atom. And with a molecular orbital, the 2 electrons would be 1 from one atom and 1 from another atom.
I like this train of thought. An atomic orbital brings 2 electrons from that atom, but a molecular orbital brings 1 electron from each atom. It's going to look that way, but it doesn't have to be that necessarily. Think about orbital, which is what? Brenna, right? Where the electrons are. And if it's an atomic orbital, it means that those electrons belong to that atom. They're just around that atom. If it's a molecular orbital, it means the electrons are? They belong to the whole molecule. the electrons are not localized to a specific atom, they're localized to a molecule. What do you need to have a molecule? We talked about this, right? Right? Good. At least 2 atoms, at least 2 nuclei. And to make a molecular orbital, you're going to need atomic orbitals. That's where we'll start. So atomic orbitals, electrons are localized to that atom. Molecular orbital, the orbital spans at least 2 nuclei, minimum, but sometimes more. All right, I've given you guys some diagrams. The first one that I'm going to sketch actually doesn't help relate to this one quite a lot. I want to show you guys the MO diagram for molecular hydrogen. These MO diagrams have 3 lanes. On the left-hand lane, we're going to show one of the atoms. On the right-hand lane, we're going to show the other atom. And in the middle, we're going to show the bond that they make. Hydrogen is a good starting point because it's very simple. Hydrogen only has the 1s atomic orbital. So on each respective lane for hydrogen, we show the atomic orbital that it comes with. We said earlier that these atomic orbitals can overlap. And that's what valence bond theory calls a bond. But we also said to make hybridized orbitals, you overlap these other orbitals, change the math around them, and get a new orbital out. So why doesn't that happen when these orbitals overlap with each other? It does. Valence bond theory just ignores it. Molecular orbital theory considers what happens when these orbitals come together. So in terms of energy, which is what we're plotting along the y-axis here, if 2 orbitals come together constructively, the energy of the resulting orbital will be lower. 2 orbitals in phase, both plus or both minus, overlap and become a lower energy orbital. If those orbitals overlap out of phase, they overlap destructively, they interfere destructively, and the energy of the new resulting orbital increases in energy. If I took an s orbital and an s orbital and I overlap them, I think you guys will agree that I should just get a larger kind of oblong sphere. But this time, there's 2 nuclei located within that orbital. It is an orbital that spans the molecule, molecular orbital. Deal? But orbitals don't have to come together in phase. It is appropriate that the s orbital can be written with plus or with minus. So kind of like the quadratic formula, you get both options. They come together where they're both plus and both minus. That's constructive. They come together where each one is out of phase. That means that instead of having this sum together and give me one large orbital, they're actually going to subtract from each other. And I'm going to get 2 separate lobes in this new orbital. This is going to look something like this. You might notice it looks a little bit like a weird p orbital. Yeah, the p is nice and tight in the middle. This one looks more like it has a bite taken out of the middle, but it has 2 lobes, like the p orbital, one shaded and one unshaded. All right, earlier I asked you, what would you call those hybridized orbitals if you had a chance? Well, here they finally had a chance to come up with new names. And instead of calling it like S plus S and S minus S, they named them for what types of bonding character they present. The constructive orbital is named sigma. This is what we call a bonding orbital. And yes, this is the same symbol, sigma, for what we called single bonds, because that's the character that it produces. When they combine destructively, we produce sigma star, which is anti-bonding. Anti-bonding. If electrons occupy a bonding orbital, MO theory says a bond exists. If electrons occupy an anti-bonding orbital, MO theory says a bond breaks. Valence bond theory cannot tell you why a bond breaks. It also can't tell you why a bond forms. MO theory can tell you why a bond forms and why a bond breaks. So let's say two neutral hydrogen atoms, each with one electron, come together. One electron here. Just to be consistent, because these are going to form a pair, I'm going to show opposite spin on my other hydrogen. I can't have two spin ups come together. I need one spin up and one spin down. If these electrons start in the atomic orbital, and then the atoms get close enough for their orbitals to combine and give molecular orbitals, the Aufbau principle says that they will move to the lowest possible energy. That is now this new sigma orbital. Why do atoms bond? Because it's energetically favorable for them. Why do atoms break their bond? There's two reasons. I can excite this lone pair, not a lone pair, sorry. I can excite this bonding pair to a higher energy orbital. Now that the electrons are in the anti-bonding orbital, the atoms don't know they're bonded and they drift apart. Or I can break this bond by taking electrons from some other species and putting them into this available orbital on top. Again, electrons occupy this anti-bonding orbital. The atoms don't know they're bonded to each other, and the bond breaks. MO theory tells us why bonds form, why bonds break. Okay. I do want to give you guys some perspective too. This always confused me when I learned about it. If electrons are only down here, then why are we talking about electrons up here as well? If this orbital is what's relevant, why do we even talk about this orbital? It's because it exists. The math for it exists. Whether it's occupied or not, orbitals are useful because they tell us something about electrons once they get there. Orbitals, these shapes, the math that defines them, they help us predict what is possible. For instance, if I wanted to put electrons into here, I actually am going to need an orbital that has this type of shape. Ideally, a p orbital, or something that can overlap with this orbital to create a bond. I love MO theory. It's a little bit heady. It's really cluttered, but it is super useful for explaining why things happen. It's terrible at depicting structures. Valence bond theory does a great job at structures, but it fails to explain the why. MO theory does a great job with the why, but it struggles to justify the structure. All right, let's take a 5-minute break. I'm going to talk to you about pi bonds in MO theory. Let's come back at 6:10, 5:10, 6:10. Jordan, welcome to the class.
Thank you.
I had to fight for you.
I'm so happy you did.
I'm glad you made it in.
Yes, me too.
The wait list never moved. Yeah, so it wasn't going to happen.
I appreciate it.
Oh no. Oh, I should wait till he comes back, but I figured out what my protein is.
Oh, you did?
It's called Syntha 6, which is kind of funny,
That one.
given our class is going to have a lot of synthesis.
Right. This is quick and simple. I brought one for you and your partner. So you
Oh,
can try one.
thank you.
They're so good.
Okay, so you just open it and chug it?
I actually don't usually use those to drink. I use them. I do in my Ninja Creamy. Wasn't I talking about?
Oh yeah, yeah.
But people rave about them. I just drink these. They're amazing.
You know, so when I was in college, I was like small. And I was like, I think I need more nutrients in my life. I ate a lot of frozen pizza and mac and cheese.
Fair.
And Culver's.
Nutritious.
And so I would go out and buy those like protein shakes. They're so disgusting.
These?
I don't know. I don't know
I'm
this.
gonna bring you one of these next year.
Maybe 10 years ago, maybe things have changed in the last 10 years, but
These are so good. Do you like chocolate milk? Yeah.
I don't really like chocolate milk, but
Well, do you like? Okay. Then
I do like chocolate brownie.
Okay, I was.
Brownie batter especially.
I don't know if it really.
It's a good way of getting salmonella. What's your favorite way of getting salmonella?
Cookie dough.
I just eat
Yes.
straight up raw chicken.
So do my cats. Anytime we cook chicken, we like carve them off some raw chicken and they go crazy for it. They've started anticipating it. So now it's gotten to a point where when we start cooking in the kitchen, they like all congregate waiting for whatever raw meat we're gonna give them. And we like switch between chicken and beef. And we used to give them both. Anytime we cook, we'd put chicken or beef. They stopped eating the beef. Costco beef, for whatever, they just won't have it. They'll come up, they'll get all excited, they'll sniff it, and they'll walk away. But the chicken, they'll come back for seconds. They are. What can I say?
Ever make raw chicken? It freaks me out.
Well, how do you make raw chicken? All you have to do is open the bag. Oh, you never buy raw chicken. You never work with raw chicken. It grosses me out too. As soon as something touches the raw chicken, it gets washed.
Yeah.
My hands, I'm washing my hands 5 times working with raw chicken. Syntha 6 is the protein that I make. Have you ever heard of it?
Not familiar.
Me either.
Okay, but does anyone have protein that doesn't use whey because lactose issues?
Not me, sorry.
Alright.
There's definitely plant-based protein.
Well, I know they have that, but like, does it taste good?
Just drink hummus. Hummus is full of protein.
Yeah, but it's not good. It's nasty to drink it. Okay.
I think it'd be great.
At this point, just tell me to eat lentils, okay?
Okay, I'm just trying to make sure I understand this. So, because it's tetrahedral, we have 3 sp2 like configurations available, right?
I think you miscopied this.
Oh yeah.
The C to H is S to sp2, because hydrogen can't be anything other than S.
Okay.
Okay, and I didn't hear what you said because I saw that.
No, that's good. That's right. Okay, so S. Okay. Carbon is gonna have 3 sp2 allowances basically.
Good.
Okay, so 1 here, and 1 here.
I
So
like that word
means-
allowances.
Yeah,
That's a good way of
it's like that
phrasing it.
cooking
Like
in my
where,
brain.
what can it use?
So then we have one other one that's not accounted for, which is our pi bond.
That's right.
How do I know that it's like PP?
If it's pi, it's P.
Okay.
If it's a pi
I
bond,
get
it's P to
that
P overlapping.
for like this class, but like
Sure. Okay,
it's
then
like not
then we
clicking with everything else. if
we
that
step
makes
back and we say on the second row of the periodic table, elements are filling S, P, P, and P orbitals.
sense. Okay.
They have 2 electrons to go in S, 2 electrons to go in PX, 2 to go in PY, 2 to go in PZ,
Okay.
which is a total of 8 electrons, our octet rule, yeah? So carbon has only used 2 of its P's, which is why we call it sp2. Although maybe the better way to call sp2 would be to call it SPP,
Okay.
because that's what the 2 is saying. It's saying that there are 2 P equivalences in this hybridization.
Okay.
Where's the other P? Those atoms on the periodic table, they have
Another p orbital.
3 P orbitals. So
Okay.
so where is
And
it?
so that's just speaking about like this bonding region here because we have that sp2 here, which is 2 P's, so there's another P available which goes there.
Yeah, so carbon, in theory, has S, P, P, and P.
Okay, yeah,
But it doesn't use them as S, P, P, and P.
right.
Instead, it uses it based on its bonding environments. Here, it has 3 bonding regions, or oxygen, 3 electron regions. So how does it want to use its allowances of S and 3 P's? Well, it's going to take S and 2 of the P's, and it's going to turn them into something new. Something that's more useful than what those 3 things were on their own.
Gotcha.
It's going to make them all into 3 equivalences of the same thing, sp2.
Okay.
And carbon is going to use 1 to make this bond. It'll use a second to make this bond. And it'll use the third of that new orbital type to make the sigma bond with O. That leftover p orbital that it never used, it uses to make the pi bond with O.
Okay.
Oxygen does the same thing. Has those S and 3 P's, takes S and 2 of the P's and turns them into something new, 3 equivalences of it. It uses 2 of them to hold the electron pairs, 1 of it to make the sigma bond with carbon, and then that last p orbital that it didn't change uses in the pi bond.
Okay. Okay. That makes more sense. Thank you.
You bet. Draw what? Oh, no. It'll be horrible to look at. I feel like the problem with drawing these orbitals overlapping is that they look terrible. So, all right, we're gonna pull back in. I'll take a step back to show you guys what these orbital overlaps look like a little bit. Hydrogen only has s orbitals, so these are just spheres around hydrogen. That carbon originally had 4 orbitals, s and 3 p's. The orientations that those provide to carbon are just not useful to minimize electron repulsion during bonding. So it reorients its capacity for those electron orbitals, and it changes them. Takes the s and 2 of the p's, and it creates something new, 3 equivalences of the same thing, leaves 1 of the p's behind. So one of those sp2 orbitals overlaps with 1 hydrogen. Another of those sp2 orbitals overlaps with the other hydrogen. The third of those sp3 orbitals goes up to overlap with the oxygen, which is in a very similar place. It has sp3 that it's using to place its lone pairs in. I drew those at weird angles because they should actually look like this. This is where it gets messy. So S to sp2, sp2 to sp2, and where is the pi bond? It's this p orbital and this p orbital overlapping. That's even the hardest one to do because technically those p orbitals are going in and out of the plane of the board. And then they're overlapping like this, but I can't show it to you very well.
Is the oxygen behind the
Well, no, right now the oxygen is in the same plane as the carbon. Okay, but now I've tilted it. Here's a wedge, so that's a hydrogen coming towards you. Here's a dash, that's a hydrogen going away from you. So now the p orbitals are actually the plane of the board. I've taken this molecule and I've rotated it like this. I've pulled it out of the plane of the board and I've laid it down as a sheet of paper. So the p orbitals, I'm trying to draw them close to show that they're overlapping. The p orbitals overlap like this. Again, those hybridized orbitals they're overlapping like this. It gets really messy really, really fast. By the way, shameless plug for this YouTube channel, Veritasium. Any of you guys watch Veritasium? Oh, you should watch. So good. They just posted a video on how they filmed electrons moving around in orbitals. And to give you some context, electrons move so fast. Do you know how fast? Crazy fast. The speed at which electrons move around is on the scale of attoseconds, which is 1 × 10⁻18 seconds is an attosecond. And for scale, there have been 4 × 10⁻17 seconds in the 13 billion year lifespan of the universe. Universe is 13 billion years long. That's 4 × 10⁻17 seconds. So the attosecond is to the second what the second is to the scale of the universe. So electrons move around at this scale where to exist for a second for them would feel like you existing for the lifetime of the universe for 13 billion years. How crazy is that? If electrons are conscious, their conscious behavior, and that's a whole other topic, sorry. If they are conscious, their experience of the universe would be like ours to the scale of the universe. Their experience of a second, 1/1000. They just lived the lifespan of the universe. That's how fast they move. All right, you should watch that video. I don't know, it's their most recent. I think it's called 1 quadrillion frames per second or something. Their most recent video, they just posted it Monday night. I watched it instead of being here with you guys. Did that help, Annie?
Yeah.
Okay. That's how the orbitals are overlapping. It just gets really messy.
So when are you going to teach quantum physics?
No. Physics, I'll pass. Here's what I want to cover next, because they don't cover this in physics. Let's look at the MO diagram for sp2 hybridized carbons coming together to form a carbon-carbon double bond. Okay, now we just reviewed this, so can you tell me what 4 orbitals does an sp2 hybridized carbon have? No, it's not 4 sigma bonds. It started with 4 orbitals. It ended with 4 orbitals. It started with s, px, py, pz. What are the 4 orbitals it ends up with? Well, those are the bonds it can make. But the orbitals that it has, sp2, 3 times. And then p. So each of these atoms is going to have 3. And by the way, if you're drawing this, it should look a little bit like this. You're going to want to give yourself space. Leave a lot of space above and a lot of space below. 3 orbitals that are all sp2 hybridized. And then it has 1 orbital that is p hybridized. Can you tell me if that p orbital lies higher in energy, equal in energy, or lower in energy to the hybridized orbitals? P lies higher because P is higher than S, so anything that hybridizes with S will be lower than P. Yeah? A combination of S and P will lie in energy between S and P. So 1 p orbital up top. Now, I think you guys can agree with me that these 2 carbons are going to bond to other things. So I don't need all of these orbitals in this example. In fact, 2 of the hybridized orbitals will be used to bond to other things. So I'm going to ignore those. And we're going to look at the p and sp2 that are needed to create the sigma and the pi bond. Just like we looked at with C to O. There's a sigma and a pi. I need sp2 to sp2 overlap. I need p to p overlap. That's what we're going to look at with these. MO theory can be quantitative. This is going to be qualitative. MO theory says that when head-on overlap occurs, you get more volume of those orbitals overlapping, and so you get a more drastic decrease and increase in energy. So when my sp2 orbitals combine constructively, I go very far down. When they combine destructively, I go very far up. You have images of this on your worksheet. My sp2 orbital has this type of shape. So when it overlaps head-on to create a molecular orbital, it's just going to be a big lob with two little ears on either side. That's what you guys see down here on your molecular orbital diagram. One big lobe in the middle with those two ears sticking out. It's a bit different than the sigma orbital made from just S, but that's because sp2 is a little bit more complicated than just S. When they combine destructively, it looks like two sp2 orbitals pointed opposite of each other and with opposite shading. We'll call this sigma when it's bonding, and sigma star when it's anti-bonding. When the p orbitals come together, they overlap side to side, which means they don't get as much volume overlapping, so the change in energy is not as drastic. The p orbitals come together constructively a bit, and they come together destructively a bit. When the p orbitals come together constructively, you get essentially one very wide p orbital, but for simplicity's sake, this is often just drawn as two p orbitals next to each other. It just gets really hard to show the big orbital. When they come together destructively, it looks like two p orbitals next to each other, but out of phase with each other. The pluses and the minuses are out of alignment. The shading and unshading don't line up. What should we call this bonding orbital created by two p orbitals? Pi. In the same way that the head-on overlap gave us a sigma orbital, the new side-on overlap gives us a pi orbital. When occupied, it leads to the formation of a pi bond. So that orbital is called pi. And what do we call the anti-bonding orbital? Pi star. Now again, we're going to look at how electrons will fill. So imagine each carbon atom comes with 4 electrons, 4 valence electrons, all spin up on one of the carbons, all spin down on the other. Don't forget that 2 of these electrons from each are going to be used for other bonding. We're ignoring them. I have 4 total electrons that I'm going to fill into my MO diagram. Aufbau principle says start from the lowest energy and fill up. Hund's rule says half fill every orbital of equal energy before fully filling. And then Hund's rule says make sure that they have opposite spins. So first electron goes into sigma, the lowest energy. Second electron pairs in sigma. Third electron goes into pi. That's the new lowest energy. Fourth electron pairs in pi. So I have created two new bonds, a sigma bond and a pi bond, because I have electron pairs occupying a sigma orbital and a pi orbital. MO diagram now explains things that Lewis structures and valence bond theory cannot explain. First of all, if I told you to look at our structures from before and I asked you, what's higher energy, the sigma bond or the pi bond? What told you that? Did valence bond theory tell you the pi bond is higher energy? Right, MO theory explains it. So let me ask you this. Looking at a Lewis structure, what's going to break first? A pi bond or a sigma bond? Is there any way to know? They're just lines. And we don't even distinguish which line is the sigma and which line is the pi. MO theory will tell you. And we use something called frontier orbitals. Frontier orbitals are the ones that do the chemistry. This here is the highest occupied molecular orbital. Where are the highest energy electrons? The highest energy electrons will do the chemistry. The highest energy electrons are in the highest occupied molecular orbital. We call this the HOMO, highest occupied. If any electrons are going to leave this system, it's the highest energy. So what bond would break first, sigma or pi? Pi, because it's the pi orbital that is the HOMO. This pi star is the LUMO. That's the lowest unoccupied orbital. If new electrons are going to come into the system, if another chemical species donates electrons to the system, Aufbau's principle says they go to the lowest energy available. That's pi star. If pi star is occupied, the pi bond breaks because it's a pi anti-bonding orbital. So LUMO says which bond will break first when new electrons are given, sigma or pi? Pi. Valence bond theory cannot justify why pi bonds break first. Only MO theory can justify why pi bonds break first. Vivi. Well, a one electron anywhere is a radical. And radicals are highly reactive because they are missing a spin partner. So generally not good. There is a component to MO theory I don't care to get into, and it's used to calculate bond order. When you look at a Lewis structure, you can say that this is a bond order of 1 between the two carbons. This is a bond order of 2. There are 2 bonds. MO theory can give you that. You sum all of the orbitals in bonding orbitals, all of the electrons in bonding orbitals, subtract all of the electrons in anti-bonding orbitals, and then divide by 2. And you can calculate the bond order. In this case, it would be, for hydrogen, 2 minus 0 divided by 2, a bond order of 1, which agrees with the Lewis structure. In this case, it'd be 2 plus 2 minus 0 divided by 2 is 2, which agrees with the Lewis structure. But it actually, and let me show you this, it actually does lead to very cool things. When you look at the MO theory of oxygen, you guys may know oxygen classically has a sigma and a pi bond. What you don't know about oxygen is that it actually has 2 pi bonds. It has 2 pi molecular orbitals filled, and then it has the equivalent of 1 pi antibond, which negates one of the 2 pi bonding orbitals that it has. So we calculate that O2 has a bond order of 2 because it has some antibonding electrons. Lewis structure would never suggest that it has 2 pi bonding and 1 pi antibonding orbital. MO theory predicts it. The other thing that MO theory predicts is that oxygen has these radical electrons, which is why in biology you want to be careful about oxygen because you have those free radicals. But also it means that oxygen is magnetic. It has unpaired electrons that have their own magnetic spin. The thing is, oxygen just doesn't have a lot of intermolecular forces, so it doesn't experience it a lot. But if you cool down oxygen enough to get it to be a liquid, liquid oxygen will bend in a magnetic field because it is attracted in a magnetic field because it has unpaired electrons, which are just little magnets. Did that answer your question? Okay. What other questions on MO theory? Yes, Kirsten.
So you said that the highest occupied would be pi, so the pi would break first. So do we, based off, because we know about MO theory, we could assume, based off the valence electron theory, or valence bonds theory, that the pi bond would break first if there is a pi bond present?
Yes, so with MO theory in mind, and again, it's hard to draw MO theory. MO theory doesn't help us draw a molecule. With MO theory in mind, we can come back to valence bond theory and Lewis structures, and we can make easier predictions about reactivity. Did that answer your question?
Yeah, I guess you said that you won't spend a lot of time on molecular orbital, it's more of like understanding the why.
It will help us understand the why.
So it's not that we need to understand the, well, okay. Yes, I think that.
Okay, and we'll keep coming back to it. Throughout the semester, I'll use MO theory to justify things like resonance, bond breaking, bond making, stability of different cations and anions. You will see a question on it in the unit test. It's very simple. It's more so about helping you identify the terminology. And what you have on this worksheet and on these notes is all you need to know. It's truly not going to be the hardest part. Okay. We're going to wrap up Unit 1 by talking about bond line structure. You maybe have seen bond line structure in the past. It's a method that we use to simplify chemical structures. Lewis structures become far too complicated, far too time-consuming, and just cluttered. They steal from some of the analysis we can make on a compound. So, first I want to cover condensed molecular structure. A condensed molecular structure essentially takes the Lewis dot structure and ignores the bonds. It groups the atoms that are bonded together, but then it doesn't show you what bonds are actually there. So actually, let's take this first example on your worksheet, molecule number 1 at the top under Lewis structure. This is hexane. It has 6 carbons. The Lewis structure is given to you. You're welcome. I didn't have you draw that one because it is tedious. Do you agree? There's a lot going on. The condensed molecular structure says there's a CH3 group on the left. And then after that, there's a carbon with 2 hydrogens, and another CH2, and another CH2. I guess I messed up. That's not hexane, that's pentane. Oh, no, it is. I'm just having a hard time interpreting it. See, the Lewis structures, they steal from your ability to interpret. There's 4 CH2 groups before you get back to another CH3. So this is how we can condense it. There's another way we can condense it, which is to say if I've got repeating units, I can put those in parentheses and give a subscript for how many of those repeating units I have. Deal? Condensed structure, not my favorite. You won't see it from me very often, but sometimes it saves space. Sometimes it's just the best way to do it. There are some groups of atoms in condensed molecular form that are written a bit uniquely. So I want to give you guys some common patterns. If you see a 6-membered ring, which represents, maybe I should have come back to this, which represents carbons at every end and bend, and hydrogens attached to them. I'm going to explain this. I am sorry. This 6-membered ring with 6 carbons can be abbreviated as C6H6. But if one of those hydrogens is pulled away to make space for a bond off of the ring to another group of atoms, then we get this ring bonded to something, and we call it C6H5, and then we can show it bonding to the rest of the structure. So C6H5 is a common condensed molecular structure that you'll see for this ring. I want you to get familiar with it because you will see it throughout the semester. There's actually another way that we represent it, and we're going to come back to it in section 3 after our first unit test. But we'll use some letters to help abbreviate it. If you have a carbon double bonded to an oxygen and also bonded to an OH group, this is often condensed as COOH or CO2H. We do the same thing when instead of a hydrogen attached to the oxygen, it's another carbon chain or another group of atoms. We can say COO, the rest of the molecule, or CO2, the rest of the molecule. I'm pointing this out because going from the condensed structure back is not always intuitive. A lot of students see this OO and they imagine that those oxygens are bonded to each other in sequence. And they're not. They're actually both bonded to the carbon. So CO2 does a better job of saying that carbon is bonded to both oxygens, not that the oxygens are bonded to each other. Some other similar ones. When this CO double bond is bonded directly to a hydrogen on the carbon, CO double bond with an H coming off, we abbreviate this as CHO. Rather than calling it COH, because we're going to show a lot of OH groups where oxygen and hydrogen are bonded to each other, and we don't want to confuse it with an OH group. So we say CHO to remind you that the H is bonded to the carbon, as is the oxygen. The hydrogen cannot be the linker between the two. Hydrogen can't make 2 bonds. So this is a way of reminding you H to C, O to C. The last one that's a bit odd, also similar to this. When we look at a carbon double bonded to oxygen, and let's just say that it has other stuff, the rest of the molecule are, there's no hydrogen, there's no oxygen groups. This often gets abbreviated with the oxygen in parentheses, which is to say, this oxygen belongs only to the carbon before it, and it does not belong as part of a sequence carbon to oxygen to carbon. Otherwise, it gets a little confusing. Looking at the oxygen mixed between two carbons, you'll think that it's a linear chain. Again, similar to how students think that this is a linear chain of oxygens. That parentheses helps to remove some of that confusion. Yeah? Okay, those are some common condensed molecular structures. Any questions on them? I should have done them second. Bond line structures are what we're going to use 90% of the time in this class. Bond line structures operate with a few assumptions. First, assume carbon at every end and bend. I don't take credit for that. I had a student that came up with that terminology. I used to say every time a line terminates and every time there's a vertex in the line, which is a lot more wordy. And enough hydrogens to satisfy the octet or charge. We do not have to show the carbons. There will be a lot of them. We don't have to show the hydrogens. There's often twice as many hydrogens as there are carbons. We can assume all of these now. You need to practice working with these assumptions, because later in the semester, you will be asked to interpret structures and understand how many carbons are there, understand how many hydrogens are there. So I want to give an example working with this assumption before we move on to some of the others. How many carbons in this molecule? 4. 3 ends, all of those sticks that just terminate, and there's one bend right there in the middle. 4 carbons. How many hydrogens? 10, 9, 8, 9. So we want to satisfy the octet, which for carbon means give it 4 bonds. All right, this carbon here explicitly has 1 bond shown. It's missing 3. So there must be 3 hydrogens. Again, that's a CH3 group. And that's true all the way around. But this carbon in the middle explicitly has 3 bonds and a positive charge. That positive charge results, you remember the table we did? That positive charge results because carbon is short a bond. No hydrogen at that central carbon. So 3, 6, 9 hydrogens in this molecule. This in the middle is just an empty C.
Will you ever see a structure drawn that way and it doesn't have the positive resulting charge?
Good question. No, because later I'm going to tell you, you can never assume charges. You have to always show charges. All right, I do want to clarify again. You don't have to assume the carbons and hydrogens, but I don't want you to nitpick, or cherry pick between them. So this is an appropriate way to draw a 4-carbon chain. This is also an appropriate way to draw a 4-carbon chain. You can see that I've now explicitly showed the 2 carbons on the end and their hydrogens, while still assuming the carbons in the middle and their hydrogens. But this is not an appropriate way to draw a 4-carbon chain. At the ends, I've just got C, no H's. Am I meant to assume the H's but not assume the carbons? You can do one or the other. Assume the carbons and the hydrogens, or show the carbons and the hydrogens, but don't show one and assume the other. Does that make sense? So avoid this because it's really hard to interpret. Rule number 2. Never assume heteroatoms or the hydrogens they bond to. What's a heteroatom? Good. Anything other than carbon and hydrogen. So can you give me an example? Oxygen. Nitrogen. That's not it. There's more. Come on, we're burning daylight. Silicon. Sulfur, phosphorus, boron, all of the halogens. Those are things you always have to show, and any hydrogens that are connected to them. So here's another example. That's a 3-carbon chain and an OH group. Notice that I've explicitly shown that H. This is not an appropriate way to show that molecule. If you're assuming the H bonded to the O, I didn't know that because we didn't agree on that assumption. Rule number 3. Assume lone pairs, but never assume charges or radicals. In fact, I might encourage you not to assume lone pairs. The advice that I get from students at the end of the semester is, or the reflection I get from them is, I wish I had shown all my lone pairs, because it just helps them understand a little bit more about what's going on in their structure. I might not show all of my lone pairs all semester. We worked on that table together last week. We had the lone pairs in that table. So you are able to start assuming what lone pairs are there. Take, for example, this oxygen. I have assumed 2 lone pairs on that oxygen. I have not shown it. But what I can never do is assume the formal charge. I have to always show formal charge. The reason is, if you have one piece of information, you can determine the other. But if you are assuming both pieces of information, you cannot determine either. If I give you the formal charge, I can figure out the lone pairs. And if I have the lone pairs, I can figure out the formal charge. But the formal charge is important. It tells you that it's an ion. So we always show formal charges. Your homework for this weekend is to translate all of these 8 structures between their Lewis dot structure, their condensed molecular structure, and their bond line structure. When we start next week, we'll work on finishing these all at once. If you're going to skip anything, skip the bond line structure, because it's tedious and it's a lot. But if you want the practice, knowing that you've fully interpreted a bond line structure, then you need to draw the Lewis structure. All right? Have a good weekend. I'll see you on Monday. We're going to get moving into section 2 on Monday.